Okay. So as discussed in the last class, I said that slowly, let us get into the second year syllabus. When I say the second year, I mean grade 12, I mean the syllabus which is which you're going to confront, you're going to get confronted as you move from your 11th to 12th. Why is it pushed into the 12th? This particular area which I'm going to teach you, which I call electromagnetism. Why is it pushed into the 12th? Is because it needs a certain basic level of mathematics. It needs you to be exposed in geometry. It needs you to be exposed in a certain area of calculus. Then you can easily kind of grasp and handle this area. So all of you who haven't yet picked up enough of calculus and enough of geometry, I think all of you should get into these areas on your own and not wait for your institution to really deal with them. Because your institutions have started the second year syllabus and they've not bothered to finish a lot of mathematics which is supposed to be done. So it's a crazy kind of a mess which is being created. It gets created every year, but you should get wise about it. You've gone through a couple of months of your institution and it becomes important that you understand that yes, these chaps are going to give us 30%, so it's better that we create a self-study program at home, get our books, the list of books which are going to help us get those books on your table and make a simple timetable, stick it on your wall and follow those books and follow the assignments, good assignments and good problem sheets so that you cover the syllabus on your own. You don't have to wait for things to be done in your institution. People who just depend on their institutions normally never make it into a good institution. So I advise people to get into a self-study program. Yes. Now, if we look at our physics syllabus, really, which is covered in the 2 years, then you will find that the entire first year is what somebody like me would call mechanics, where the property mass is kind of stressed on. I would take an object and I would say that take an object A which has a mass m1. See, I immediately assign it a property called mass. And then I go about applying my laws of mechanics. When I say laws of mechanics, what I mean is Newton's laws. And then slowly as I move from one dynamic situation to other, from simple motions to motions which get a little more involved, where collisions are involved, explosions are involved, or I get into still further involvement where the object goes through a rotation, and then it gets more involved where I take an object and immerse it in some fluid, and then my object oscillates, vibrates, etc. So as I move into different dynamic situations, I continue to apply the Newton's laws by kind of readjusting them, manipulating them, and I slowly develop number of simple fundamentals which help me analyze these dynamic situations. That is how I went about mechanics. Similarly, when you come to the second year, when you come to the second year, we suddenly find that we start talking of the property charge. Symbols used are this or this. And we soon, as we get into this area where charge is stressed upon, we take a particle, the particle is going to have mass. But now we start talking about the other properties of this particle and we speak about charge. There are many properties a particle has. It's not that there is only mass or there's charge. There are many intrinsic little situations happening inside a particle or an object, which give them other intrinsic properties. But our syllabus at 10+2
So we couldn't hear you.
Oh my God. I'm sorry, please hold on. Can you hear me, please?
Yes, sir.
Yeah.
Yes, sir.
I just went out for a few minutes, or was it not there at all?
For a few seconds.
Just for a few seconds. My God. I got the feeling that I was just talking to myself. Can you hear me clearly now?
Yes, yeah.
Yes, sir.
Okay. So when we look at our syllabus, we find that almost 40% of our syllabus is covers what we call mechanics, and around 50% is an area which is developed around the property charge, which I call electromagnetism. So when I say I'm going to start the second year syllabus, I'm speaking about this area, electromagnetism. Please understand. Yes, Hitesh, you're trying to tell me something, Hitesh?
No, sir, that was a mistake. Sorry.
No, please don't do that because that disturbs me very badly. Yes. So we have the property M. If we even recollect a little, because we'll be drawing a lot of analogies between the two. If you look back and try and understand what really you are doing in mechanics is, if you say, we took an object, of course, we called it a rigid body. So we had a rigid body which had this intrinsic property mass. What we mean by intrinsic is that if we break this rigid body into small pieces, Each little particle that you pick up is still going to have mass. As you keep reducing the size of these particles and reach the size of an atom, the atom is still going to have a mass. And if you go further into the atom, into the atomic particles, whether you go to the electrons or you go to the protons or you get into the nucleus and look at the protons and the neutrons and further get deeper into smaller and smaller particles, you will find that they have this property mass. That's exactly what we mean by intrinsic. You can't get rid of it. The same thing, we're going to talk about charge. That if we were to take a particle, let us say a coin, which you remove from your pocket, you will find that it has charge. You break the coin into smaller and smaller and smaller and smaller and smaller pieces, you'll find that it still has charge. Go into the atom, still has charge. Deep into the atom, still has charge. Deep into the nucleus, it still has this intrinsic property charge. And you'll be surprised that this intrinsic property charge, just like this intrinsic property mass, created an entire area, what we call Newtonian mechanics, Newtonian physics, what we call mechanics. This property mass played a very big role. Similarly, charge, you'll be surprised, is responsible for electricity, is responsible for magnetism, is responsible for the electromagnetic wave, which is light. It is this intrinsic property charge. Okay. Having accepted that, let us go into a little bit of history on how this very property charge came into being. Means how it was noticed, it was always there, how it got noticed, and who are the people, main people behind it, who really gave it a firm rooting. This will cover almost 50% of our syllabus. And if I were to compare electromagnetism and mechanics, then let me tell you something, this is a much easier chapter. The examiner cannot twist too many things around in this chapter. The problems are pretty straightforward. The only difference between the two is that you have to remember quite a few things. Whereas in this, there was nothing. There was one core law, the Newton's law, which was the law of mechanics, which said that the net force is proportional to acceleration. Acceleration is nothing but a change in motion. And that was sufficient. And knowing 5 forces, basic forces, which Newton listed for us, they were sufficient for us to understand practically the entire mechanics. Here, you will find that as we move from area to area within electromagnetism, starting with electrostatics, and then we move into current electricity, then we move into magnetics, magnetism, then we move into electromagnetism or electromagnetic inductions. And as we keep listing the different phenomena, and along the way, we will use these phenomena and properties to design different electrical elements like the capacitors, the resistors, inductors. As we move, we find that all these little phenomena and developments are all because of the intrinsic property charge. It's amazing. You will be surprised that take the example of light. This whole phenomena of light that the sun sends down to us, and all kinds of other phenomena which are noticed, whether you say dispersion when you look at a rainbow, these natural phenomena, the formation of shadows, then actually experiencing a reflection and an image formation when you look into a shiny surface, which we call mirrors. All these phenomena which came about because of reflection, refraction, dispersion, etc., were discovered much before people really understood electromagnetism. Right from the time of the 17th century, when Newton started really listing down his laws of mechanics. Being a theoretical physicist, Newton even spoke about light. In fact, he created certain properties of light. He himself listed them, and he was able to explain simple phenomena like reflection, refraction, etc., without knowing the nature of light. So, a lot of phenomena were being mentioned, a lot of rules and laws were being laid down in the chapter of light, starting from the 18th century down, 1700 and something, and maybe earlier. But the nature of light was not understood. We went right down 17th century, 18th century, 19th century, 1800 and something, 19th century. Slowly, people started understanding the nature of light. So many hundred years. Lot of things were already written about different phenomena of light in the chapter of optics before, without them knowing the nature of light. It was only towards after mid-19th century that great people like Maxwell slowly, theoretically, tried to convince the scientific community that light was an electromagnetic phenomenon. It was only towards the end of the 19th century, with experiments done by Hendrik Hertz, a contemporary colleague of Maxwell, maybe a student of Maxwell, who, using the theoretical notes of Maxwell, conducted certain basic experiments. Hertz was an experimenter. He was able to clearly show to the scientific community through his experiments that what we talk about light on an everyday basis, what comes from the sun, is basically nothing but an electromagnetic wave, an energy wave, which is nothing but a disturbance of electricity and magnetism, each generating the other. Look at it. end of the 19th century, we got to know the nature of light. Once the nature of light was understood, suddenly the entire scientific knowledge exploded. Sophisticated equipments came into play, optical equipments. Lot more experiments got generated, resulting in the creation of wonderful products. In fact, it was after the mid-19th century, which is 1845 down to 1875 and towards the end. And then 1900, end of the 19th century, beginning of the 20th century, during Einstein's time, that suddenly there was a real huge explosion in scientific knowledge and sophisticated equipments. So, if you look at the end of the 19th century and beginning of the 20th century, Einstein often made statements like that today I'm able to say and I'm able to prove and I'm able to explain a lot of phenomena around is because of the works done by Newton and the works done by Maxwell. He often referred to Maxwell as the father of electromagnetism, and he referred to Newton as the father of mechanics. He said, I'm standing on the shoulders of Newton and Maxwell, Einstein. And I'm just putting down what they had discovered. So understand where we are. We are just starting our discussions on electromagnetism, and we are going to, through various phenomena, understand this intrinsic property charge. And as we understand charge, and as we make the charge go through different dynamic situations, that means we take a particle or an object which has a charge and make it go through various dynamic situations, we are able to see all the phenomena that we experience in electricity and magnetism around us. Okay. So let us develop this area of electromagnetism as it is put down in a certain chronological order for us by the community of scientists. Let us expand it. Let us go into certain very basic little events which are not really necessary for us to go very deep into. We'll just mention them so that it gives us in the head a certain sequence in which we have to move. If we accept the fact that there is something called charge, I will use the symbol small q. If I accept the fact that just like the intrinsic property mass, there is another intrinsic property in every material, every matter, in every object, in every particle called charge. So when I take a particle, when I say particle, what I mean is something quite tiny whose dimensions I cannot define, I call a particle. So if I take a particle, then if I write this, it is fair. I'm just trying to highlight these two intrinsic properties, knowing very well that there might be many more intrinsic properties that I don't talk about in my syllabus. Fair enough, so I keep them silent. Just like when I was in the chapter of mechanics, I kept charge silent. I only spoke about mass, though charge was always there. Now, in this chapter, I will not talk much about mass, but I will from time to time mention it because I already know quite a lot about mass. So when I take a particle and I write in a bracket Qm, I'm trying to tell you that I would like to have both the properties in my problem because both are going to play a role. Okay, yes. We have accepted the fact that just like mass, there is a property charge, which is intrinsic. You can't get rid of it. Do you mean to say that if I take out a coin from my pocket, can I say this coin has charge Q? No. This coin has millions of charges, but they are balanced. What do you mean by that? Okay. So let us go back into history. Then if we go back into history, we'll come across names like Benjamin Franklin, not that before him, nobody else noticed what he had noticed. There must be a number of people who must have noticed that when they take two objects and rub them together, they find that these objects, once you rub them, take them apart, and then you take them around different dirt particles, you find that they attract dirt particles. Even as a kid, I had noticed that. But we only remember people who are able to quantify, who are able to clearly define these little phenomena. Benjamin Franklin was one of them. He spoke about this intrinsic property charge, and he told us that there are two kinds of charges. He said, unlike mass, which is of one kind, charges are of two kinds. The entire committee of scientists left it to him. Said, all right, you can name these two charges that you have noticed. You convince us first there are two kinds. So he carried out these little experiments and convinced them that, see, there are two kinds of charges. And they gave him the authority to name them. He called one kind of charge positive and the other kind negative. If it was in some other country, the scientists there would have called these two kinds of charges something else. But then Benjamin Franklin was the first. So today we all accept the fact that there are two kinds of charges, positive and negative. This is just a name given by Benjamin Franklin. Beautiful name, positive and negative. And then through his little experiments, he says that like charges, when you bring them together, they will repel. Unlike charges will attract. Fair enough. That means when you talk about repulsion and when you talk about attraction, you're talking about some kind of a force, a pull, a tug, or a push, which Newton called a force. So there is a force when you bring two charges together. Like charges, there is a force, it repels. Unlike charges, they will attract. So a plus and a minus will attract, a minus and a minus will repel, a plus and a plus will repel. We still haven't explained what is charge. That coin in my pocket, I said, had millions of charges. But when you ask me the question, sir, does your coin have charge? I said, no. Because when we say that a particle has charge, we mean only the excess charge. We don't mean the millions and millions of balanced charges in the coin. They are balanced. There are equal number of pluses and minuses in this coin. So it doesn't interest me. It is a neutral particle. When I say this coin has been charged, that means some excess charge has developed on it. And that excess charge is what we call Q. So when I say a particle, I take a particle and it has got charge Q and mass M. What I mean is that it has got an excess charge Q. It could be by itself having millions of charges, but they are balanced. I only talk of the surplus charge. It could be positive, it could be negative. If we were to go down to the very basic of a particle, let's say an atom, today, not then in the 18th century, today, we know in an atom is a neutral fellow. It's got equal number of positives and negatives, correct? But we know very well also, if we accept today the hazy structure of the atom given to us by whatever modern science we have, then we know that there is a very dense positive area, and outside you have a negative cloud. It is the scientific community which laid down the entire science for us students. They told us that let the charge outside be the negative charge and let the charge inside be the positive charge. In an atom, it is balanced. Now, if I remove some negatives, this has an excess positive, because to start off with, they were balanced. So if I remove some negatives, which is very easy for me to do because it's just a cloud outside, it's called excess positive. How easy is it to do it? Here, look at my hand. Look at my finger. If I were to check this zone, it would be having excess positive. I've actually erased off the negative, assuming it was neutral. It's so easy. But if I leave my hand in this environment for some time, and then I check, I don't see the charge. It's got neutralized. The negatives in the air settled down, got attracted by the positive, excess positive, and it got neutralized. Generally, in life around, there is a balance. In this entire environment around me, there is a balance, generally a balance. If at all there is an imbalance, there will be some localized areas where there will be some excess charge in this environment. But otherwise, generally balanced. Know this. So when I say a particle has charge, always remember it's the excess charge. So if I remove a few negatives, it's excess positive. If I put a few negatives, it becomes excess negative. And I only talk about that excess, that addition or that subtraction, that bit. Number one, try and understand this. And understand the fact that there are two kinds of charges. Most of us know that. Another thing. If I take this particle and I look at the excess charge, let us say I have a way of measuring it, which you will learn as you move into electromagnetism. You will learn all these things. Let us say I have a way of measuring it. Then to my surprise, I find that as I keep reducing the charge, I reach a point, and then if I reduce it further, it goes to zero. Next step. It suddenly jumps to zero. From zero, when I'm trying to put charge on my particle, it suddenly jumps from zero to a value. That means there is no continuity in it. That means this charge that I speak about, let's look at the excess charge, is a multiple of a certain small value to which I give a symbol E. Then the smallest value of charge, to which I give the symbol E, is called the quantum value of charge. And we say charges are quantized. That means they can be expressed in multiples of the smallest charge. Let me accept the fact that apart from Benjamin Franklin, who contributed to us understanding charge to a certain extent. And definitely to give him credit for convincing us that there are two kinds of charges. We gave him respect by saying, okay, Benjamin Franklin, you name these two charges, and he called one positive, one negative. Fair enough. There were other people who contributed. Once Benjamin Franklin had made it clear that there is a force when you bring two charges together, like charges will repel, that means there is a push. Or when you bring unlike charges together, there is an attraction, there is a pull. Then there are other people who studied these forces, the value of this force. They quantified this force. They built up a relationship between two charges coming together and the force. And one of them was Coulomb. Because Coulomb successfully quantified charge, quantified the force between two charges, whether it is an attractive force or repulsive force, because he spent a great amount of time trying to understand this force, this electric force. He's given respects by naming, by taking his name and attaching it to charge. So we said that we measure charge and the measurement unit is Coulomb. In the International System of Measurements, the Committee of Scientists said that let us name the basic measuring unit of charge after Coulomb. So it's called coulombs. So when we say that we have a particle having charge 3 microcoulombs, coulombs, 3 microcoulombs, then 3 microcoulombs can be expressed in terms of multiples of E, where E is the smallest value of charge which exists. Now let's be clear. You can have particles, when you break up electrons, you get something called quarks. And maybe you can break up quarks into smaller particles. I don't want to get into that. And that is not our business right now. But if we can break up, let us say we come to electrons or protons, and then we break them up into quarks. Probably quarks have smaller values of charge. But honestly speaking, when you break up a proton into quarks or an electron into quarks, within no time, you get back your proton or electron. This is only for a fraction of a microsecond that you are able to see the quarks, and then they disappear and you only see protons and electrons. So we still consider that our smallest units as we go into the atom are going to be electrons, protons, etc. Let's come back. So when we accept the fact through various measuring experiments that the smallest value of charge is 1.6 into 10 raised to minus 19 coulombs. This value was found, you will soon see, by Thomson. And he is given credit for that. I will come to these little experiments. Let us accept the fact that the smallest value of charge in terms of coulombs, now that we have established the measuring unit of coulomb, measuring unit of charge as coulombs, and if we say that the smallest value of charge is coulombs, is 1.6 into 10 raised to minus 19 coulomb is the smallest value of charge, and we give it the symbol E. And anything smaller than that is 0. And hence we say that charge jumps up in multiples of E. Then this we say is the quantum smallest value, the quantum value of charge, which is 1.6 into 10 raised to minus 19, and we give it a special symbol E. Then whatever charge we take, say 3 microcoulombs, it has to be in multiples of E. Many years back, there was a question in the exam. Students were asked to find out a value of a charge. So they did various elaborate calculations depending on which chapter they were in, and they found the value of charge through various calculations. That value was less than this. And then you were given 4 keys. And one of the keys was 0. The correct answer was 0. Anything below this you have to put 0, because there is no charge below this. You are supposed to tick the answer 0. Because from 0 then, the next value that comes is 1.6 into 10 raised to minus 19. And then what comes is multiples of 1.6 into 10 raised to minus 19, that is multiples of E. There is no name given to it. It's just a symbol which says that when you write this, it means the smallest value of charge. Yes, subsequently, as various other scientists were studying the structure of material, and then they were getting into molecules and atoms, etc., etc., that was a different field altogether. They gave the charge value to the electron as 1.6 into 10 raised to 9. And they said that the electron and the proton have this value, which is the smallest value of charge. That is a different study. Let's not get confused about it. We are in the chapter of electromagnetism, and we are trying to understand a very, very important intrinsic property, charge, which gives rise to this phenomenon, electromagnetism. So great. So we said charge, this is excess charge, is quantized. Charge is quantized, and when we say a particle is charged, we only mean that excess charge, and whatever the excess charge is will always be in multiples of E, where E is the quantum value of charge, whose value is 1.6 into 10 raised to minus 19 coulombs, is the basic measuring unit of the charge after the works done by Coulomb. We have covered that. Don't get too much deep into it. As you read different reference books, somewhere on the side an illustration will be there as to the little experiments done by Coulomb or Benjamin Franklin. No problems. You can read them. You don't have to get into the science of it right now. And in fact, you'll be surprised, the experiment which was done by Coulomb to find out and quantify the value of this force, I will give it to you as a problem. So great. We have accepted the fact that our entire electromagnetism is going to revolve around this property charge. And we say that when we say that a particle has a charge Q, we are not talking of the millions and millions of charges which that particle has, which are balanced. We are only talking of the unbalanced charge. And we say, when we say that our particle has a charge Q, we are only talking of the excess charge. And we said that our excess charge has the smallest value E, the quantum value of charge, which is 1.6 into 10 raised to minus 19, and the measuring unit is coulombs. So any charge, that excess charge that we put on a particle, it could be a particle, it could be a spherical object, it could be a coin, it could be a piece of cloth. Any excess charge on these objects will always be in multiples of E. And charges are of two kinds. And like charges, positive positives will repel, and unlike charges will attract. Good. Let's move forward and talk about the works done by Coulomb. Coulomb carried out an experiment using a torsional, or you can call it torsion balance or torsional balance. Why torsion? Is because he used the property torsion. Torsion means when you twist, let's say you take a wire and you twist it, you're creating a certain stress inside the wire we call torsion. And when you release the wire, it will rotate back into its original state. That twist, that torsion, that twist you create in the wire. So he used a simple experiment, which we call a torsional balance. I don't want to get too much deep into it. And he quantified, which I will take as a problem, I told you, this particular experiment. And he quantified the force between these two charges, Q1 and Q2. What do you mean by that, charges? I took a particle, I put an excess charge on it. I took another particle, I put an excess charge on it. I brought them close enough, and I experienced the pull or the tug. Or the push. They experienced a force. If they are both positive, then we draw a line through the two particles. Why are we talking of particles? Why don't we just take two spherical objects? We will. Let us first, to focus more on the property charge, let us not give any dimensions to our object. Because the moment I say spherical, I have to give it a radius. The moment I say it's a rectangular block, I have to give it certain dimensions. I don't want to do that and get lost in it. I take two charges, which are on two particles, just 2 points. Very small particles, the dimensions are not important. I put excess charge Q1 and excess charge Q2. Let us say both are positive. Then according to the study done by Coulomb, great study done, he said that you draw a line passing through these charges, then if they are both positive or both negative, they will experience a repulsion. And along the line joining these two particles, they will experience an equal and opposite force, which he called an electric force. We will use the subscript E. Equal and opposite. Which means if we take this as a system, this is an internal force which gets balanced. Okay, all right. Each particle experiences, which has excess charge, experiences a force. That force in magnitude, according to the experiment done by Coulomb using a torsional balance, was found to be proportional to the product of the two charges, was found to be inversely proportional to the square of the distance between the two charges. And when the proportionality was removed, Coulomb magnitude only, put us little k, and he says Q1, Q2 upon R square. Coulomb, during his time, never had the exposure of the entire huge area of electromagnetics. Magnetism was being studied by different committee of scientists, and so was electricity, and so was electromagnetic induction, and so were many other things. Different groups were studying it. Each group had their own measuring units. Nobody even in their right minds thought that electricity and magnetism were nothing but the same phenomena. Nobody knew it during Coulomb's time, including Coulomb. He studied things in clean isolation. Once he had accepted, once he had learned how to charge particles, he took two particles in the torsional balance, which is a very simple experiment at the ends of a rod, and then he brings two charges together and he sees the twist of the wire and things like that, and he measures the angle and things like that. I'll get into it later on. Right now, we are not getting into it. We are just saying that Coulomb was the one who quantified the forces between charges, and he got this result, and he got this formulation, and he had quantified the force between two charges, Q1 and Q2, separated by a distance r. And he said this force in magnitude is along the line joining the two particles, and if the two particles have the same sign, have of the same nature, positive, then they will experience a repulsion, equal and opposite. Each particle, charged particle, will experience the Coulomb's force. Units of charge, coulombs. Unit of this in the international system, meters. And units of force, newtons. This was a very, very limited discussion had during Coulomb's time. Soon Coulomb realized that when he took two particles in air and found the force, and then he took the same two particles in a different environment, some gas, or in a different location, he found this force changed. This had not changed, this had not changed, this had not changed. Then how come the force changed? That means something was happening here. Those of you who've been with me when I was teaching you the chapter of gravitation, where we were trying to understand the intrinsic property mass, then if you recollect, there also a very similar experiment was done. The torsional balance was used to quantify the force between two particles having the property mass m1 and m2. This force we call electric force. That force we call gravitational force. Newton called it gravitational forces between two particles m1 and m2. If I go into that discussion, which I will in 2 minutes, you will find that the discussion is almost the same. But let's be very clear. Though I am studying electromagnetism in my second year, and I studied the gravitational law in the first year, this experiment was done much before the experiment which was done to find the gravitational force by Cavendish. Newton only made a statement. Newton was a theoretical physicist. Newton was not an experimenter. Based on Newton's ideas, Cavendish carried out the experiment using a torsional balance. And he quantified the gravitational force, that attractive force between the two particles m1 and m2. But that experiment that Cavendish carried out, which was based on the same kind of apparatus, the torsional balance, that was done much after what Coulomb had done. So in fact, maybe Cavendish used these ideas, I don't know, maybe he used these ideas which Coulomb had put down, and he carried out his experiment. Who knows? In those days, it was very difficult to communicate unless you were in the same country, in the same region. The communication levels were absolutely zero. There was no way to really find out what was happening in different countries. Fair enough. Let us put down that experiment which Cavendish did. Let us put down that result, what we call Newton's law of gravitation. This is called Coulomb's law of finding the electric force between two charges. I will further modify it. Let us look at that experiment, which was done by Cavendish on instructions of Newton, that if you take two particles having the properties m1 and m2, separated, these two particles are separated by a distance r. Then when these two particles are brought close enough, which have the intrinsic property mass, then they will attract each other. By a force we call the gravitational force. Equal and opposite. It is always, the gravitational force is always an attractive force. The Coulomb's force, depending on the sign of Q1 and Q2, whether this is positive, this is negative, will be attractive. If these both are positive, it will be repulsive. but the formula remains the same. So it can be an attractive force, it can be a repulsive force, but the gravitational force is always an attractive force. When you join the two particles, then the force is along the line joining the two particles, just like this one. And when it was quantified by Cavendish, he said that the gravitational force in magnitude is proportional to the product of the two intrinsic properties. Product of the two intrinsic properties. Inversely proportional to the distance between the two particles squared. And when the proportionality was removed, in magnitude, we put here a G. If you go back to that discussion in your head, then if you recollect, I told you this was a simple mathematical proportionality constant which balanced the left and the right. The universal constant G. It just balanced the left and the right. It had nothing else. Two particles, M1 and M2, separated by a huge obstruction, will still have the gravitational force this. This was just a mathematical constant balancing the left and the right. But Coulomb realized that there was something off. He took the same charges Q1 and Q2. He separated them by distance r, but he had changed the environment. He found that the electric force value had changed. In a vacuum, it gave him some value. In air, it gave him some value. In some other gas, it gave him the third value. For the same two charges, for the same distance. Then this was changing. This was changing depending on the medium. This was not a simple mathematical constant, balancing the left and the right. This had something else in it. It was very, very much unlike the gravitational constant. Coulomb didn't know how to handle it. Much later, as electromagnetism moved and developed, with contributions from Faraday, contributions from Maxwell, different experiments done by various other scientists. Slowly, K started taking a form. If I, with my simplicity, just put a K on and say this is the Coulomb's law, and give it some value when I say that Q1 and Q2 are in a vacuum, give it some value. And I move on in life. So I moved on in life. I developed one area called, let us say, electrostatics, where the charges are under static conditions. Slowly, this electric force, we started qualifying it, and we started calling it electrostatic force. Coulomb's electrostatic force, because the charges were under static conditions. I took two charges, Q1 and Q2, excess charges on two particles, Q1 and Q2, and I kept them under static conditions. They were not moving. Yes, once I brought them together, they started moving. That's different. But to start off with, they were static. I call that electric force static force, electrostatic force. Then, under static conditions of charge, I developed an entire chapter called electrostatics. Then I moved charge. I developed an entire chapter called current electricity. Moving charge is nothing but, we say, electric. Now, electric current. Once charges move, we say we have an electric current, rate at which charge is moving with time. And through a section of a wire, we say that so much of charge has moved in so many seconds. Then when we take the ratio, we say that's the electric current. Whatever, we'll define it later. Then, Coulomb did not understand this K. Let us say, with the ignorance that Coulomb had, I also continue to just treat K just like G. And let us say I move on. From electrostatics, I start moving charges, I develop current electricity, and then I start looking at moving charges generating magnetism. I move into magnetism, and then I move into electromagnetic induction, and then I move and move and move, and I come, let us say, to the end of electromagnetism. Holding on to my K. Then you will be surprised that if I were to do that, then I find this K as I move from electrostatics into the next area, current electricity. Slowly this K, as I move into magnetism, as I move into electromagnetic induction, as I move into electromagnetic phenomena, look at what is happening to this K. It has started looking like a devil. This simple K, to make life easy for myself, I said, let this K be as simple as G. And as I moved this K into current electricity, it developed horns. As I moved into magnetism, it developed ties. As I moved it into electromagnetic induction, it developed ears. And as I moved it further, it developed sharp teeth. It became a devil. It became unrecognizable. And towards the end, at the end of electromagnetism, when all phenomena were defined and now I'm supposed to smoothen out and simplify my life, it became more complicated. This K grew so ugly that it became very difficult to handle it towards the end or analyze it. This was exactly the problem. The people, the committee of scientists who put down electromagnetism by taking K as one simple K, just like G. And as they moved, they realized that this K took forms which became uglier and uglier and uglier and uglier. And towards the end, they themselves were finding it very difficult analyzing this mess because they made life easy for themselves in the beginning. Then that committee sat down and they said that, see, we have to give the student of science a certain chronological order of this chapter of electromagnetism so that he picks up the vocabulary as he moves and moves and moves, and towards the end, the entire electromagnetism beautifully gets rounded off and becomes simple. If we were to do that, then we will have to distribute this ugliness throughout electromagnetism in small bits and pieces so that towards the end, as this ugliness, these horns come in the chapter of electrostatics, these ears comes in magnetism, this sharp teeth come in induction, etc. As we distribute this ugliness, when we move to the end, we get a simple, crisp conclusion of our chapter of electromagnetism, which is electromagnetic waves, light waves. To create that, they distributed this ugliness throughout the entire area of electromagnets. Some of it went into electrostatics, some of it went into electricity, some of it went into magnetism, some of it went into electromagnetic induction, etc., etc. And when towards the end, it became a very simple alphabet like K. This is one thing you will have to understand. I do not want any one of you using K because your sirs use K. Don't ever do that. Or your textbooks use K. Don't ever do that. We will put down Coulomb's law in its correct format, which Coulomb didn't know, by the way. It was that committee of scientists, much after Coulomb had left. It was the committee of scientists which put down the order in which things were to be distributed, a certain order in which it was to be presented to the student of science. We look at it that way. And so, when we now slowly accept the fact for the time being that the entire chapter of electromagnetism is going to be based on this intrinsic property charge, if we accept it. And then we quickly move on to the Coulomb's law. Keeping in mind all the things that we know. The charge is quantized, it's in multiples of 1.6 into 10 raised to minus 19, and the measuring units of charge are coulombs. All that is fine. That's perfect. Charges are of two kinds, positive, negative, all fine. But when we put down the Coulomb's law, which is basically quantifying the force, between two charges. It becomes important that we put it down in the correct form. So if we have two particles having charge Q1 and Q2 separated by a distance r, then the electrostatic force, because the charges are under static conditions. Who did that? I kept those particles static. And hence, the electrostatic force in its magnitude is proportional to Q1, Q2, inversely proportional to R squared. And when I remove this proportionality, I get this term. You might tell me, my God, 4 pi epsilon naught. 1/4. What an ugly guy. Coulomb didn't know about it. I had to distribute the ugliness. Little here and little there and little here. You'll come across weird terms whose explanation you won't get 100% now. But as you move, you will slowly realize what a wonderful term this 1/4 pi epsilon later on as we move on. You will get to know the meaning of epsilon naught actually towards the end of electrostatics. And that too, it was given by Faraday. For the time being, we accept that the Coulomb's force in newtons is proportional to the product of the two charges Q1 and Q2, which are measured in coulombs, and inversely proportional to the square of the distance between the two. And when you put that force, remove the proportionality, you get a term 1.5 epsilon naught. When the charges are in a vacuum, then the term epsilon naught, this is 4, this is pi, normal, geometrical 4, pi, epsilon naught, that's how it's called, is called permittivity of free space. Very difficult term to absorb right now, right in the beginning of electromagnetics. Yes, but you write the Coulomb's law in this format. I don't want anybody putting K. I'll tell you why. Where epsilon naught is the permittivity of this free space, that means permittivity of the vacuum. What is this permittivity? Some kind of permission, permittivity. See it this way, that if I have a charge Q, let us say I have a switch. I put the switch on, charge Q comes into play, let us say, in this environment. I switch it off, it's gone. I have another charge here, Q naught. Q naught has no eyes, nor does Q have any eyes, nor do they have ears. But when I switch on Q, suddenly this guy experiences a tug. How did this chap know so that he starts moving that this guy is there? How did he know? I switch it off, this guy is quiet again. I switch it on, this guy experiences a tug. Maybe a push or a pull. Which means when I switch on this, even if this guy wasn't there, the moment I switch on this property, charge, the region in this area, all round, of course, experiences some kind of an influence because of the presence of this property charge. When I switch it on, suddenly the region is different. The space around is experiencing, just like we said in the chapter of gravitation, that if we have the Earth, then this person here experiences the property M, mass. He experiences a tug because he has the mass M. Because he has come under the influence of the Earth. Because he has come under the gravitational field of the Earth. So the moment M naught came within the gravitational field, it experienced a tug. The moment Q naught came within the electric field of Q. Okay, Q is static. Electrostatic field of Q. You can say electric field also. Because charge is static, we'll say electrostatic field of Q. Q naught came under that influence and hence it experienced a stun. Then, when I switched on the property Q, the environment around went through a change. This change that the environment goes through is something to do with the permittivity. Right now, you'll have to view it like. So different media will behave differently in presence of Q. In a vacuum, the behavior is represented by epsilon. If the medium is anything other than a vacuum, we will say epsilon. That time we will write down the force between Q1 and Q2. When we write down the Coulomb's force, we will use epsilon. What will that be? Then epsilon will be permittivity of the medium, not free space. When they are in a medium. When they're in a vacuum, we'll say epsilon naught, and we'll say permittivity of free space. What is this permittivity? We haven't understood it yet clearly. It has something to do with the influence. It is something to do with the changes the environment goes through because of the property Q. Permitting this property Q to influence the media, something like that. Let us accept that for the time being, because we are just starting our study of electromagnetism. Then slowly, after 3 or 4 lectures, you will understand. Because you might ask me, how do you find out the value of this for a media? Epsilon naught for a vacuum, epsilon for a medium other than a vacuum. How do we find out these values which we will require in this formulas? Yes, that is exactly what you're going to find out after 3 or 4 lectures. This is the unfortunate bit about electromagnetism. Electromagnetism had devious ways of discoveries. Somebody was working on magnetism with different measuring units. Somebody was working on electricity with different things. Somebody was working on light with different kind of measuring units, and everybody was, there was a mess. Later on, the committee put everything together, and then they created a chronological order in which the student of science was to be given the chapter of electricity. And in the process of doing that, they had to introduce terms which took a meaning later on. You please accept that. Don't try to get a meaning of this today from me, because then there'll be other vocabulary terms which I'll have to explain, which will come slowly. Then you will understand the meaning of this word epsilon naught, called the permittivity. Epsilon not permittivity of species, or epsilon is permittivity of a medium. I want you to write the Coulomb's law like this, which quantifies the force between 2 point charges, between 2 particles. I am not saying, you don't say between 2 objects. No, between 2 objects, it will not be this formula. It is only between 2 particles. Very good. Very, very good. A lot of information we collected. The moment I change the media, I'll just change this. And the examiner will give me the value of permittivity of that media. No problems. Right now, I'm defining the Coulomb's law in a vacuum. This particular term takes a wonderful value. Epsilon naught has a value, approximate, I'm telling you. What are the units? Just bring this here, take everything there, these units, coulomb, square, meter square, Newton, all that. I will just write SI units. Approximately 8.85 into 10 raised to minus 12. Okay. Soon you will realize that 1 upon 4 pi epsilon naught, even if there is a 2 here, we will never cancel that 2 and this 4. We will leave it as it is because this has a wonderful whole number, which I'll tell you subsequently in the next class. We never cancel any terms from here with the adjoining things because this itself has a wonderful simple number which we can use and easily multiply our other factors. Don't ever cancel this. 1 upon 4 pi epsilon remains as it is, or 1 upon pi epsilon. Another thing to be mentioned at this stage, that supposing Q1 and Q2 were in a vacuum, and I calculated for the same distance r, same charges Q1 and Q2 distance r, I calculated the Coulomb force. Then I removed the vacuum and I put air. Obviously, I put epsilon there. I found that the Coulomb's force now, in case of air, comes down. Now, the force between Q1 and Q2 became less than what it was in a vacuum. What does it tell me? It tells me that epsilon is greater than epsilon naught. The permittivity of the medium is greater than this. Yes, true, yes. The moment I change from vacuum to any media, air, water, oil, gas, etc., glass, whatever, I find that the permittivity of the media is always greater than epsilon naught, and hence I'm putting a greater value in the denominator. Hence, the Coulomb's force always reduces in a medium compared to a vacuum. That. Very good. Once we have put down the Coulomb's law, once we have understood how to write the formula for quantifying the force between two particles under static conditions separated by a distance r, and we call this force the electric force or the electrostatic force because the charges are static. We now understand that after all, if we are talking of a force, we are talking of a vector. Then, sir, we have a charge Q1, we have another charge Q2, we have a third charge Q3, and I want to find out the net electric force on Q1. See how I'm writing it? This is for my own purpose. I'm studying science for myself. I'm studying science so that I understand it. Electrostatic force on Q1 or electrostatic force net on 1. Then, if this is positive, this is positive, this is negative. Then I join Q1, Q2, positive, positive. Then one experiences F12 in this direction along the line joining this. Then between this and this, I join this. Then between this and this, it experiences an attractive force, this. F13 this. Then the net on this is the resultant this. Fair enough. We know this much. We will, when we have to add the forces F12 plus F13, we will, as usual, add up vectors by resolving them into x and y components, then add up all the x's, add up all the y's with the correct plus minus sign, and then find the resultant square root of fx square plus fy square. I will get the magnitude of the resultant force. And if I want the direction, I will find the direction with respect to any one of them using my simple triangle laws. Okay. What if this charge is far away? If it's far away, there is no force between. When it comes closer and closer and closer and closer, at some distance r, suddenly Q2 comes within the influence of 1, comes within the electric field of 1, and hence experiences a tug. Then Q2 also has its electric field. That means the two electric fields merge, no problems. A very complex phenomena could be developing as two charges come together because each one has its field. No problems. We are not getting into that. That's a very high level study. We are trying to keep it as simple as possible. We have two charges separated by a distance r. What charges? Particles. Point charges. The formula is only for point charges. The Coulomb's law is only for point charges. The Newton's gravitational law was only for point charges. And later on, the point charges were developed into spherical objects. And then those spherical objects were developed into planets. And then only Newton started talking about the gravitational forces between planets, etc. Same thing we'll do here. There are millions of charges around you, but they are balanced. It is very easy to create an imbalance. See, I just rubbed my hand and the skin is charged. Maybe I just brushed off the outermost electrons from my skin and it became excess positive. Positives were more than negatives because some negatives got thrown out. Then some negatives from the air came because of the attractive force between positives and negatives and neutralized my skin. No problems. We will generally make a statement that this is how we charge two bodies. It's a very small, minor element of the discussion. Once this is accepted, then what was the idea? The idea was to understand this intrinsic property charge, to understand what this charge does, how it influences the medium around. The idea was to get deep into that. And by getting into the depth of the influence created by the charge, we get to know our charge better. So, without wasting any time, we immediately launch ourselves into developing two wonderful ideas based on this force, which will give us a richer information on our intrinsic property charge. Let's just do that right away. Once I've given you enough knowledge and vocabulary on this charge and then on the electrostatic forces, etc., 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 that I will take up some applications. Till then, it's a waste of time. Let me say that when I take two charges, Q and let us say Q naught, separated by a distance r, I get a force, electric force, because charges are static, electrostatic force in magnitude equal to 1/4 pi epsilon naught. That means I've taken a vacuum. This is pi, please, into Q naught upon r squared. I'm going to use this and slowly float two wonderful ideas. One is based on the field concept, which is a vector concept, where I'll talk of an electric field, giving it the alphabet capital E with this. And using this concept, I'll be able to map the influence of charge in a medium. So I will develop the field concept, and then I will use this and develop a scalar idea This I call the electric or electrostatics. It's not really necessary. Electric field concept. And here I will develop the idea of electric potential or electrostatic potential, because the charges are static. Electrostatic potential, electrostatic field, or just electric field, electric potential. I will develop these two ideas based on this. Let me right away start this. These are my two charges. This is what I've got. Let me get rid of Q naught. Mathematically, there. I removed it from here, I took it. I'm still in a vacuum, so epsilon naught. Newton force per coulomb. This I call magnitude magnet. The electric field, the electrostatic field. What do you mean by that? I got rid of Q naught. There. Remove it from here, put it here. I got rid of Q naught. I only have Q in my formula. At a distance R, at a point P. This now I call a source. And that point P, I call it a field point. I switched on the source. And this whole region got influenced, got electrified. An electric field got established. An electric field got established. So at P, I have a field at a distance R. Electric field got established, which is proportional to the intensity of the source. I double this, the electric field gets doubled. It's directly proportional. Half it, the electric field gets half it. What is this electric field? Influence that this intrinsic property has created in the medium. It's proportional to the intensity of the source. It is inversely proportional to the distance R squared. As I move, the electric field drops drastically. I was at 2, it dropped by 4. I moved at 4, it dropped by 16. What? Its influence. Field value dropped. E proportional to this, E inversely proportional. But E is a vector. How do I get the direction of E? This Q naught, intentionally I have taken Q naught. Q naught is the symbol we normally give to what we call a test charge. In the chapter of electromagnetism, the test charge is quite important. It has been defined specifically by that committee of scientists that a test charge is always a positive charge. As the nomenclature which has been set up in the chapter of electromagnetism, that when we say we are taking a test charge, it will always be positive. And the value of this charge tends to 0. It is very, very, very small, which means a test charge does not have its own field. It cannot influence a media because it is very, very small. It is just a test charge. And it is always positive. So, to get the direction of the electric field, magnitude I've got. To get the direction of the electric field, I need a tester. I take my test charge and I put it here, which is always positive. If this guy was positive, then this tester along the line joining this would experience a push, repulsion. Then this becomes the direction of the electric field at this point. It doesn't mean that the electric field is traveling this way. Electric field does not travel. Just like gravitational field does not travel. You switch on the mass of the earth and the entire region around gets influenced, and that influence we call the gravitational field. And if any other mass comes within this gravitational field, it will get pulled towards the earth. Gravitational force. Same. I switch on the source, and if the source is positive, then the test charge which I put here, tester, always positive. Tester, if this is positive, then it will experience a push. That becomes along the line joining the two. Remember, we are talking of only point charges. This becomes the direction of the electric field at this wheel point P. If I was here, it would have a value E dash, and it would have this value. Why E dash? Because its value is different, because E is so I can take the tester. And these little arrows, when I join them, I get the map of the influence, the mapping of my field. For who? For this point charge. Similarly, I can take point, line charge. Similarly, I can take this line, make it into a loop. Circular charge in a loop. I'll find out my mapping. For different configurations of the charge, I will find out the electric field. I will find out the potential once I've defined this. Right now, I'm defining and how to go about life mapping. Now, this is a very important thing about general human beings, that when we normally show a line like this and then we do this, then we have a problem with our mind. We feel that this means that whatever is there is flowing this way. See, it comes automatically to us. This is very wrong. Electric field does not flow. Gravitational field does not flow. This is just a representation. What is this representation? That if you put a test charge here, which is always a positive charge, then it is going to move in this direction. It is going to experience a force in this direction. This arrow is an indication of that. This arrow is not an indication as if it is some fluid flowing. This is a question which is going to be asked in your interviews. The moment you say that the electric field is flowing this way, you are gone. You'll be kicked out. What was this? This was a concept I floated. What was it? It was just to represent the general influence around. What do you mean? I'll explain. Please, I know time is flying. Just we started a little late. Just give me another 2 minutes. That's all. Then I'll stop. I know that your sirs do not teach the subject in this manner. If you really want to do well and understand electromagnetism by its roots, then you better follow this flow, which is exactly the flow that was laid down by the committee of scientists who wanted you to study the subject in this particular flow. Whatever you are doing elsewhere, I don't know. Right. Let me take, just give me 2 minutes, not even 2 minutes, 1.5. So if I take a point charge, let us say it is positive, and I put a test charge here, 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 test charge here. And then I join all these arrows, then I get something like this. When I join all these arrows, I get something like this. I'm not finished. The more arrows you join and the more locations you take with your test charge and keep drawing those little arrows and then join those little arrows, the more you take, the better mapping you get. Now, I am now putting the test charge all around to see my influence. So I put it here, I put it here, I put it here, I put it here, then I joined all these lines. And now this arrow, don't show one arrow here, one arrow here, one arrow here, you won't get the picture. Show the arrows at equidistance so that you understand why this mapping is so important. Now, look at these arrows as a whole. If I were to put any charge, say Q dash, which is positive, if I were to put a positive charge within this region, and it's positive, see how it's going to move? The charge will experience that push. This mapping is supposed to give you that picture. If I put a negative charge here, then it's going to be pulled in. So this is the mapping for a simple point charge. You could have 2-point charges, you could have 3, you could have 4. You could have a line charge, you could have a charge on a loop. And in general, the examiner will show you maybe this, maybe something like this, and he will say this. And he will say, shown are electric field lines. The direction does not mean that they are moving this way. The direction is the direction of a test charge, which is a positive charge, will always move in the direction of these arrows. So, it is like this. Let me write down this formula. We'll discuss this further, this 1/4 pi epsilon later. Supposing I write this as this upon Q naught. I take Q naught here. When I take Q naught here means I'm putting Q naught here. So when I take Q naught here, I get the force. That's the force this guy is going to experience, which is going to be in this direction. That's all. A test charge, which is always positive. So you're supposed to put a test charge, and that is exactly how you assign these arrows to these lines. Then certain rules were made about these field lines. If they are further apart shown, that means the E here, let us say dash, and here you have E double dash when the lines are together. That means E E double dash is greater than E dash. The intensity here is weaker, so they are far apart. The intensity here is higher, so they are brought together. Rules were made. More rules were made. That if we draw the mapping like this, equidistant, the distances are the same. Equidistant and parallel, and we do this, it means the value of the electric field here and here in magnitude and direction is the same as here, as here. That means we say this is the mapping of an E which is uniform. That means in direction and magnitude everywhere is the same. But if the examiner in one of the exams he gave like this, then sir, the lines are parallel, but they are not equidistant. The E here is different from E. This is not the representation of a uniform field. He gave this and everybody took it as a uniform field and solved the problem. This is the uniform field. Equidistant and parallel. E uniform. So you want to show E uniform? You'll show it like this. Okay. Simple rules got made for the electric field. We have defined it for a point charge Q right now. What did we say? Take a charge which is the source, then at a distance R, E is proportional to Q and E is inversely proportional to R squared. That's what we said. At which point? Field point. If we want to know the direction of the field there, we will take a positive charge and put it here. If this is positive, then this will be this way. Hence, the electric field direction is this at this point P, which is the field point. And its magnitude is given by E equal to 1/4 pi epsilon naught Q upon R squared. And what are the units of E? In this case, Newton per coulomb. That's all we have learned. Then I'll take point on a string. I'll make it a line. Then I'll take this string which is charged. I'll make it a loop. And I'll keep doing that. And I will study the electric field and the potential. I haven't defined the potential. I won't do it right now because it'll take me some time. I will define it in my next class. I've just created a base right now. The base so that I'm telling you this is how I am going to make the subject flow. And I'm going to cover each and everything which is mentioned in your syllabus, but with this flow, which is the natural flow in which the subject was supposed to move. And slowly, every term will take a meaning, including epsilon naught. Every term will take a value, 1/4 pi epsilon naught will take a certain value, and we will move and move and move and move. And when we come towards the end of electromagnetism, after a series of lectures, you will be surprised that suddenly the terms start becoming very crisp and small and understandable. That is when we know we have reached the end, and now we are in a position to launch ourselves in electromagnetic waves, that is optics. Okay, sir. I will stop the lecture here.